Hi, welcome to the Signal Path. It is that time of the year again, and the International Microwave Symposium just concluded in San Francisco, California, and it had one of the largest industry exhibitions to date. So I cannot cover everything in there, of course, but I tried to go in a few different places and bring you some of the interesting things that I came across. So let's get started.
And here we have the newly released Rodenshaw's FSWX. This is a two-port spectrum analyzer. Now the very first thing you're going to ask is, why is this different than just having two spectrum analyzers next to each other? Well, the LO architecture of something like this must be really interesting because you're allowed to look at two completely independent frequencies coming at these at the same time. But because they're co-processed in the back end inside of the unit, they can run some really interesting correlation characteristics on the signal that's coming in, essentially removing a lot of the residual noise of the instrument itself, giving you this unprecedented linearity in the back end. So the correlation functions in software can then do all kind of really unusual things, removing impairments from amplifiers, understanding what happens to your DUT before and after, or if you have two completely different carriers and you want to understand what happens between them as a relationship, you can do this with these two front ports. One other thing they've done is that they have actually kind of forgo the YIG in the front of this instrument, which is a new approach in doing this. You can still get the YIG as an option on this, but by using pre-select filters on each of these independently, you get your spur removal, you get your image removal just like you had before. But now when you do complete digitization, you can still maintain that filter in the front end of the digitizer, because in the YIG system, you have to remove the YIG to do that. So now you get even better spur and dynamic range directly digitizing this. This has a 2x4 gigahertz digitizer, so essentially the same 8 gigahertz complete digitization that you have from the FSW, but here now you can split it. Gives you a little bit of insight on how they do the digitization in the back end. But there's a couple of demos that I want to tell you about that they're doing here live. But the software capability of this and what you can do in the back end, having the similar body and sharing some of the LO must be quite fascinating. This is a completely different way of building FSWX and building spectrum analyzers in general, and it's going to be a big impact on this domain. So here's a live measurement showing something that is very difficult to measure otherwise. So here we have a satellite device, which is actually a frequency converter. So we have a different frequency at the input, and after this, it's essentially a mixer. Now imagine that you want to characterize this mixer's nonlinearities, its imperfections, and its dynamic behavior under actual situations when it's transmitting a modulation, in this case a PSK, particularly for satellite. So how would you do that? Well, normally you'd have to take your reference signal, which is at the low frequency, completely analyze it, make sure you understand, and then take the output, capture that, and then compare the input and the output at two different frequencies and do all the alignments to understand what this device is doing to your signal. But here, you can do all of it at once. So the signal, the IF signal at low frequency is split at the input, fed into one channel of the spectrum analyzer. The output of the mixer is now at a different frequency. In this case, it's at 11 gigahertz. You feed that into another channel of the spectrum analyzer. Now they're in two different carriers, but everything is completely self-aligned to the front of the instrument. Now you can run coloration algorithms and understand what that mixer is doing to the signal coming in, and then that becomes a complete characterization of that nonlinear device using a single instrument, fully aligned in the front end. All of it, again, captured inside of this and co-analyzed, and you can get the phase, you can get the AM to PM distortion, and if you make any tweaks to this, LO power, biasing, you will see live changes, but it's tested under complete modulation. That is a totally different way of doing this under one instrument. So here I have another setup. This is now the Rodenshaw's ZNB 3000. This particular model, 4-channel up to 26.5 gigahertz with an extraordinary 160 dB of dynamic range and extremely fast measurement speed. The ZNB is essentially kind of like a production line kind of instrument where you can run a lot of rapid measurements. It has now compression gain measurements and everything on top of it. Now the setup here is interesting because Rodenshaw's have their own very high power amplifiers. So what you can do is you can couple something like the ZNB into this amplifier, getting extremely high output power. And in this particular test, at the very top here, a little difficult to see, but they have a very small filter and some coupler. So they are pumping in a huge amount of power into that filter and measuring S parameters over different conditions of the excitation power into the filter. So what you can imagine happens is that that filter eventually might fail, either catastrophically or non-catastrophically. It may have hysteresis effect as the power comes and goes. And using the ZNB and the filter combination, you'll eventually build this characterization matrix that tells you exactly how that filter operates under these stress conditions. So for figuring out both in lab and production environments. Now there are couplers at the top, of course, because you don't want to put that huge amount of power into the instrument. And there's also a power sensor over here using a coupler, and all of the network analyzers from Rohde & Schwarz and many of the spectrum analyzers can receive a power sensor directly at the input, measuring really accurate power. So you're capturing the power, the S parameters, and the entire matrix all in one setup, coupled with all the equipment, and you can stress test pretty much anything you want. So here we have again the ZNB, a 4-channel version, 26.5, now connected to a switch matrix. One of the interesting things about this large switch matrix is that the entire architecture of this is solid state. So the switching speed between the different ports is extremely fast. Here they have connected it to an 8-channel transmitter, 8-channel receiver beamformer. So now imagine that you can run thousands of S parameters measuring all of the characteristics of all possible combinations of these transmitters in less than 1 second. So if you want to measure active return loss, you want to find out what happens between different switching characteristics of a very complex phased array, you can do it all at super rapid speed. Now at the same time, there are bypass ports in the front of the switch matrix. So you can insert low noise amplifiers and be able to measure noise figure directly on the same setup. And this is again enabled because you have access to all of the ports. But the combination of a solid state rapid switch box and a super fast network analyzer means that you can do these things that normally would take a long time extremely quickly. And obviously advanced softwares in compression and other capabilities of the ZNB allows you to do more sophisticated nonlinear characterizations of the transmitter and receiver. And you have a complete software control, so you can also adjust the settings of your DUT while you're measuring it, basically having an automated very rapidly running system to characterize these kind of complex multi-port devices. And here I have the Rohde & Schwarz FSWP. Now this is not a new instrument in itself. It's existed for quite some time. It has an internal built-in source. It used to go up to 80 gigahertz or so, but now it has been completely revamped with built-in sources that go up to 54 gigahertz. So now you can, of course, measure correlated phase noise. That's the core strength of this instrument. With the internal built-in source up to 54 gigahertz, now you can do all that correlated additive phase noise as well using the internal source. But there's a couple of other interesting tricks you can play with the new architecture that we have here. So for example, if you inject an external source into the instrument itself, you can now measure additive phase noise up to 56 gigahertz. And here we have an example of an amplifier whose additive phase noise is being measured. But there is an additional thing you can do. Imagine you excite this amplifier with a certain power, let's say 0 dBm. Then you can find out what its additive phase noise impact is compared to the signal coming into it. Now, as you reduce the input power to this amplifier, some of the other effects of the amplifier's noise, like its white noise, begins to dominate. And that dominate tells you something about the noise figure of this amplifier. So you're measuring the noise figure indirectly by measuring correlated phase noise, additive phase noise to the amplifier. So a very unusual technique, but it is basically competing with something like the Y-factor method. Now, an internal source on this, let's say something like a 54 gigahertz synthesizer, is a very good synthesizer for a cross-correlation phase noise measurement system. But it's not going to be as good as a narrowband signal. So if you want to measure something that is super high-quality cavity at very high frequencies, what you can do is you can remove these links, add your own dual sources into the instrument, and then have the control voltage of the instrument lock those sources to the internal one. Now you've got a locked external source that can be used for additive phase noise directly on the instrument itself. And that combination now gives you a huge dynamic range of phase noise and additive phase noise capability all in the same box. Now, naturally, there is obviously supply and control voltages in here for VCO characterization, doing super fast cross-correlation up to 54 gigahertz. All those are the classic features that this FSWP has had. But it's really interesting that once you make an instrument sophisticated and advanced enough in terms of its analytical capabilities, you begin to extract unusual features like noise figure from an amplifier in a completely different way. So it's exciting to see that. Now, one little thing that I wanted to correct here is that the internal sources that go up to 56 gigahertz allows you to do phase noise cross-correlation up to 56 inherently. That's not a problem. The issue is when you want to measure above 54 gigahertz for additive phase noise with external devices, you need to route that signal out of the instrument. And in that situation, you can do it up to 54 gigahertz. That 2 gigahertz difference between them has to do with the amplifiers and the available output power. But nevertheless, having the ability to inject your own external sources gives you a flexibility in any case, because in some situations, you want to get increased speed, or you want to reduce the number of measurements you want to make to get to the cross-correlation floor, that still allows you to do that. So here we're looking at one of the yet unreleased new power supplies from Rohde & Schwarz. So if you look at the past couple of years, let's say about 5 years or so, Rohde & Schwarz has completely revamped their power supply portfolio. I have several of them in the lab. We've been using them over many different experiments, but this particular unit is now an ultra-high power unit, 1800 watts per channel, 2-channel, running from a standard 115 volt, North American plug. But of course, you may need more than 1800. And the way they've designed the thermal profile of something like this is that you can stack these. You can stack them without interfering with the airflow and the fan. But when you stack them, you can put them in series or put them in parallel and synchronize them. So now you have 1800 times as many of these channels, up to 3 of them you can stack, getting even higher power. So now if you combine something like this NGT with the other series of power supplies and the various dynamic power supplies they have now source measure units that they also have created in the past couple of years. The portfolio of power supply of Rohde & Schwarz has grown drastically, and it's just going to be yet another interesting addition. So if you remember, a couple of years ago, we recorded the Rohde & Schwarz near field, far field measurement chamber. Now this has been extended. Now I'm doing handheld here so you can actually see what's going on the inside. You can see there are multiple reflectors now on each side of this individual chamber. So the question becomes, why would you want to do something like this? Well, imagine you have a large-scale phased array, something like this, that's built in quadrants, is able to do multi-beam, and it is receiving and transmitting signals in different directions. What you want to do is you want to find out how this behaves in a dynamic environment with simultaneous beams coming in at the same time. You can have an imposing beam that's causing interference, or you may be just talking to 4 different end units and you want to see how that behaves. All of that can now actually be done inside of this one chamber because you have multiple reflectors, multiple transmit and receive units, so you can both excite and measure this array from multiple angles. Now this is obviously a pretty large setup, and even in here, you can see the control system on this can measure thermal characteristics of what's going on. It can control many, many instruments at the same time. In the back of this box, there is a stack of vector signal generators and network analyzers controlling all of these sources and exciting these arrays in different ways. And this entire module can be separated. You can actually break this up and separate it. It's not in one unit, so you assemble it on site. But these mirrors have extremely high type of tolerances because you can measure up to 110 to 170 gigahertz. So you can imagine the finish on these mirrors is really, really tight. Yeah, very cool setup, and nice to see how it's been expanded.
I'm Jeremy Woldridge with Samtec. I'm here with Shahriar, who's going to talk a little bit about why Nokia is using glass.
So glass is a phenomenal material because you're allowed to do things on glass that you traditionally cannot do on PCB material. It actually rivals semiconductor precision and capability. But glass is just a material at the end of the day. It's the processing that makes it suitable for what we want to use it. So Samtec has a very particular way they process the glass. It gives us lithography, precision, predictability of the metallization, and these amazing vias that they can put inside of the glass. In fact, this processing almost allows us to treat the glass substrate as an extension of our silicon, meaning that now we can architect our chipsets and put things on glass that you couldn't put before, and then bring an entire new performance metric from these modules. We've been working with this material for many years, have built some world record devices operating in the hundreds of gigahertz, and it's going to become the foundation platform for our next generation devices. The application isn't just in wireless. There are other domains like optical and sensors and radars and other areas which we would like to further explore. But it's really the entire processing and the glass properties that allows this. And if you look at some of our publicly available material and devices, you get an idea of the loss performance that this material can give us. It's exciting. It's a new paradigm of packaging. It's really the next step to bring these really complex mixed signal devices together.
Thank you. For more information on Samtec's glass core packaging, visit samtec.com/GCT. Thanks for watching.
So here at the Keysight booth, we're going to look at an active load pull system. Now we've talked about active load pulls in the past, and it's all about how you put the whole system together and combine it with the software to extract the parameters you want from your setup. So here we have the MXG, which is a 4-port instrument that you can have 100 megahertz of analysis and computation bandwidth that you can synthesize any waveform you want. So now imagine that I take one channel and I put it at the input of an amplifier, and I take a second channel, pass it through an amplifier and a coupler, and I feed it now to the output of my DUT. So now by playing with the waveforms and having the correlation and coherent between them, I can synthesize any impedance I want at the output of my amplifier. So now I have complete control over the load pool of this. Now you have this, now what can you do with it? Well, if you have one of these PXIe network analyzers with direct receiver access, you now can digitize this entire bandwidth in sections and then assemble that together and not only extract the EVM, but also all of the nonlinear parameters from this amplifier at the same time. And you take all those nonlinear parameters and you pass it into Keysight EDA tools. Now you have the model of the amplifier directly based on the dynamic measurements of this active load pool, put that in your simulation, and then go back and forth validating what you're looking at. So here we're combining RF synthesizers, direct access receiver network analyzers, and of course DUT and amplifiers. And they've done some pretty funny looking measurements there. They can synthesize an entire load pool that's the shape of the Keysight logo, which is kind of funny. And at the top, you can see the captured equivalent spectrum before and after, and from that you can extract EVM, and you can extract all the nonlinear parameters. You can see the compression, OIP3, and of course you can get an estimation of the EVM. This estimation of the EVM in one setup is really helpful, because normally what you'd have to do is you'd have to capture that separately, because that's a dynamic time domain based system. Here you're doing frequency stitching to compensate it, just do all that in one setup. There's a lot going on here, but these active load pool systems are now more and more common, especially coupled with simulation results. So here at Keysight, we also have another turnkey solution for measuring radiation patterns and other characterizations of the device. Now the challenge with this kind of measurements is always the same. The problem is that the measurement plane has to be moved to the edge of your device in order for that measurement to be helpful. And normally over-the-air measurements always have so much uncertainty, because you don't know where exactly happens to the reflections, where is the measurement plane, where have you done your calibration. So in this system, you're able to bring your measurement plane to the edge of your device. And that's because you can calibrate the entire system. Here at the very top, you can see that we have our near field, far field lens translator over there. So you're really measuring this thing essentially in equivalent far field. We have a PNAX on the other side, which I will show you. You can do all your calibration, bring the measurement, and then get complete characterization of the device. Then you can steer the beam, just like any phased array would. And as you steer the beam, you will see all of the imperfection of the beam. You can get ERP over the angle. You can find out what happens to the power. Now, because you're looking at the measurement plane of the device, you can also do things like DPD. You can find the nonlinearity of the device, but you're measuring it in far field. So you're measuring the nonlinearity of a phased array, which is subject to a lot of active return loss and unknown things that happen in open space. You're capturing all that in one go inside of the chamber. And here are some of the devices that are coupled with this chamber. Of course, you have a PNAX for S-parameter measurement, calibration and everything. And here's also a VXG. Now, coupling the VXG into this device now allows you to do modulations up to much, much higher instantaneous bandwidth. Now you can excite your device under test at the calibration plane that you want using high order modulation. Now you're looking at dynamic characteristics of the device during beamforming, all inside of the chamber in an isolated environment. So here at Keysight, I have the PNAX Pro. Now, even though the PNAX itself is going to continue as a product, PNAX Pro has some fundamental architectural differences inside that enable a whole other range of measurement techniques. I think it's worthwhile talking a little bit about the architectural changes so you can appreciate what this new instrument can do. So here's the overall block diagram of the PNAX Pro. Now, the first thing to note is that unlike the PNAX, we have 4 completely independent sources now inside the instrument. These independent sources can have different powers, different center frequencies, and different phase. Even though they're ultimately at some point coherently connected, you can adjust their phases with respect to each other. So now you have a network analyzer with complete control over all the parameters of all the sources, exciting your device under test. So what can you do with it? Well, a few things right away come to mind. So for example, you can route 2 of the synthesizers to one port. Now you have a 2-tone measurement. But you can now do a 2-tone measurement at the input of the device and at the output of the device simultaneously. So you can excite the device with these very interesting intermodulation effects that can come up. Now, we also have 2 completely independent low noise receivers now built into the system, each of them with a certain type of filter banks to emulate pre-select filters in front of it. So why would you want that? Well, if you have a device that's bidirectional, like a TR module, you may want to do low noise measurements in one direction and in the other direction at the same time without having to flip your device, and this allows you to do that. There's some other unusual pulsing now you can do because you have multiple sources. Now, there are some weird memory effects that can happen in devices. So applying a single pulse to a device may no longer be enough to capture some of the long-term memory effects or some unusual dynamic behavior. So what you can do is you can couple 2 of these sources to your DUT, pulse one of the sources with a small pulse. In the middle of that pulse, add another source on top. Now you get a big pulse. And then you'll see the exact memory effect between the small pulse, which sets kind of your baseline, and the big pulse, which sets your nonlinearity. And all of that can be captured again in one setup. Now again, because you have these different ports with different synthesizers, you can control the phase between all the synthesizers. You can measure IQ mixers, because you can say, now sweep for me the phase of one of these as a function of time. And then you can then see what happens to image rejection. You can see what happens to the output amplitude. How does the mixer behave under those conditions? Now there is obviously all the nonlinearities you can measure. I mean, there's just almost unlimited number of things you can do. And here you also, these sources are also a little bit different from the PNAX, because the core of the sources are direct digital synthesis based. So you have these arbitrary waveform generators at the heart of these sources, being able to generate up to 6 gigahertz of instantaneous bandwidth. So you can now excite your device with that on top of everything else that you have these independent sources working at the same time. So, I mean, at this point, you're going to have to let your imagination go wild, because once I give you all these knobs and I give you all these independent sources in there, it's kind of almost like a software-defined network analyzer. I mean, there's just so much happening. And you can mix and match and, yeah, get all kind of interesting measurements going on at the same time. The PNX Pro's architecture is different from the PNA, and those differences, I'm sure, are going to be lead to some interesting measurements in the future. So here's a quick example live demo running PNX Pro connected to an IQ mixer. You can see here on the x-axis, we are sweeping the phase. And of course, as you sweep the phase with the two independent sources, you see the upper and the lower sideband, the image go back and forth between the two of them. A very unusual measurement to see on a network analyzer, because you're looking at spectrum. And one of the other things I forgot to mention, that the noise floor here of this with the low noise receivers is now down below minus 160, minus 164. So you're looking at the dynamic range that's absolutely enormous, at the same time as all the other functionalities that are thrown in there, including the digitizers and everything. So yeah, there's a lot you can do here. And here now we have a complete D-band characterization system here running live. There's actually a lot going on in the setup, because we're simultaneously capturing a D-band signal from these radios at RF, and we're also capturing it after down conversion at baseband through the equivalent receivers. Now, because there's so many things going on, you have to make sure that you capture all of these measurements at the same time simultaneously. So here you have a 4-channel arbitrary waveform generator at the bottom. You have an 8-channel oscilloscope here at the top, capturing differential signals on a full duplex system. And then you have this VDI extender combined with the Keysight UXA in order to steal a little bit of the power at the RF and down convert that through the VDI and analyze it with the UXA. So we're doing spectral measurements at carrier frequency. We're using baseband, oscilloscope, and arbitrary waveform generators to measure all of these. Now, one challenge that comes from these kind of measurements is that the higher you go in frequency, the noise of the device that generates your signal and the noise of the analyzer that's trying to analyze your signal may actually limit your measurement dynamic range. So there has to be some clever signal processing we can throw at this in order to remove some of those noise effects. And removing them allows you to understand where the impairments of the system actually are and where they are limited. So let me show you a quick look at the IQ noise cancellation there on the instrument. So here we're looking at the screen of the VSA running directly on UXA, and here you can see a constellation here measured at a carrier frequency of 162 gigahertz. Now there's some EVM here as around 3.5 to 4% or so. Now we want to understand, well, where is the limitation coming from? Is this noise from the analyzer? Is it from the device under test? What can you do to eliminate and correct that? So with the IQ noise correction. So here we have an option to do repeated coherent measurements. Now imagine if I make these measurements over and over and over again, and every time I correlate the measurement with the previous one. That allows me to do this coherent averaging and find out what is the signal and what is the noise and subtract that. And if I do that, you can see that the EVM improves considerably. Now we're looking at EVM around 2%. Now one other thing we can do is we can capture the noise power from the receiver separately when it's terminated, and add that noise power back into the signal to see, was it the DUT noise that was limiting the EVM, or was it the analyzer noise? And if we do this, which this measurement's already been calibrated, I click on that, and you can see that the number goes roughly back to where it was. And that tells us that the majority of the noise is coming from the transmitter, and there's some phase noise and everything else that are on top of this. This ability to differentiate the source of noise and remove it from a complex measurement like this is extremely important device characterization, because it tells you where to look for problems and where to correct them. And this is now a feature that's built into VSA. So here I'm at MPI again, looking at the terahertz selection probe station. These are fantastic probe stations with multiple modules that can be added to do all kind of different automatic handling, temperature control, and manipulating the probe locations. You can see we have a probe loader, a wafer loader on the left side over here. The temperature controller is built in on the back. But I want to show you a little bit closer look in the middle, because there are some critical things that they've added to these terahertz type of measurements, which are very difficult to do normally on a probe station. And those subtleties make all the difference in having repeatable and low drift measurements. So take a look at what's going on over here. So we've seen this in the past where they have this temperature barrier with laminar airflow that allows you to cool the chalk and heat the chalk without the heat coming up and without condensation appearing on the chalk. But the problem still remains that when you land your probes on the chalk that is at a certain temperature, whether high or low, what's going to happen is that you're connecting everything with a waveguide. So that temperature is going to go into the heads. So these heads have been purposely brought in so close to the measurement to minimize any kind of interconnect. You don't want any S-band, you don't want any losses in that interface, because that's all uncertainty as well. But when you bring things closer, of course you bring them thermally closer. So what they've done is that they have this kind of thermal guard in the middle where you have a airflow going inside that cools the tip, as well as separating the actual probe from the terahertz module over here, completely thermally isolating them. And that allows you to, of course, run this at any temperature, but not pull the temperature of the terahertz converter with your actual probe, which is huge, because once you calibrate and you heat up and cool down, you don't want your measurements to drift. So these type of subtle additions to the probe stations make them really unique for these kind of measurements. So here we have one of the TS150 terahertz manual probe stations from MPI. Now, they were one of the first groups to kind of pioneer this concept that you can make a manual probe station and still bring your probe heads extremely close to the device under test. This is, of course, all mechanical ingenuity. At the same time, you have the chuck in the middle, and there are different versions of this probe station with different chuck sizes, 6, 8, and 12 inches, again, maintaining a similar manual control over everything. And here, allowing you to have a complete 3-port solution now, despite the fact that this is such a compact probe station, bringing all of those, allowing you to do things like mixer conversions, all with individual remotes that are attached to it. Now, don't get fooled by the fact that this is a manual probe station. It still has all the digital measurements. You can still do all very sophisticated calibrations on this, easy to use, and its compactness really does make a difference in scenarios where you don't have a lot of room or you won't have many probe stations next to each other. MPI over the years has kind of, in my view, a little bit revolutionized the way these things are built, because they put so much pressure on the competition because of the modularity of their probe stations. There's just so many possible configurations for whatever needs you may have. So now, despite the fact that this probe station is manual, there are a lot of kind of mechanical built-in safety features built into it to ensure that potentially inexperienced students or operators don't damage the wafer and the probes. So for example, if you have landed the probes or you have a contact, you cannot move the chuck anymore. Even though everything is mechanical, it's locked in place, so you can't accidentally scratch all your probes and everything across your wafer. You also have this contact support where you allow you to just lift just enough so that everything is in focus, but then if you raise and lower this very quickly, it wouldn't matter how fast you touch this. It will always land the probe at the same rate through the mechanical dampening systems that are built into it. So even though it's fully manual, it has a lot of the features that automatic probe stations would normally have. And here I have the lock-in amplifier from Zurich Instruments, the particular SHFLI model. And if you've watched the channel, I have done a full extensive review of the Zurich Instruments lock-in amplifier in the past, built on the Lab 1 platform, which is a fantastic software platform controlling all of their instrumentation. Now, this lock-in amplifier goes up to 8.5 gigahertz. It has 8 modulators and 8 demodulators, being able to generate all these tones up to 8.5 gig. With instrument feedback directly on the front, with all the software features, PID controllers, and everything built in. But one key aspect is that if you want to do lock-in amplification up to 8.5 gigahertz, traditionally people would have had to build down converters and up converters in front of classical lock-in amplifiers. The challenge is you're just adding uncertainty to your measurements, and you're not getting any feedback on the saturation or the compression behavior of everything you've added to your system. This abstracts all of that away, bring the measurement plane up to 8.5 gigahertz with all the demodulators and modulators to the front panel connectors. And that's a completely different system now, significantly reducing the time it takes to do these tests. So I'm really eager to do an extensive review on this. It's going to take a little bit of time because there's just so much inside of instruments like this one. But the applications in quantum, the applications in analyzing really sophisticated and unusual physical characteristics of materials in science and in chemistry and physics is just unbounded. So I'm really looking forward to it, and make sure that you subscribe so you don't miss it. So here I am at Z Communication, and if you have watched any of my videos, you know that pretty much every time we open an instrumentation device, there is always some kind of a VCO or PLL from Z Communication in there, and people often wrap their own PLL systems around their VCOs and oscillators. Now what they've also done is that they now have a whole slew of these compact modules, LNAs, amplifiers, power amplifiers, and so on, but then they also have these kind of smart PLLs, which have a lot of really useful features. First of all, these are controlled with a Bluetooth. So you can either control them with USB-C or Bluetooth or power from USB-C. This particular model has a built-in amplifier, things like phase synchronization, lock detections, and so on, allowing you to basically set the carrier frequency from your phone, from an app, and then connect it to the system you want. And the compactness, the fact that there's fully shielded, predictable output power, predictable performance, and a very wide frequency range, in this case 45 megahertz to 22.6 gigahertz. These now have become quite useful for dropping into various systems and so on. So it's kind of always nice to see, you start with some core strong elements and then you build a system around it and grow your product portfolio. They actually have a live demo of a different version of this one that I also want to show you. So here's another version of the same smart PLL. This one is a smaller one that doesn't have the output amplifier. So what they've done is that they've connected an output amplifier to it. So kind of imagine that these two combined modules is what we were looking at. And here's an app here running on a phone. So you can basically control the center frequency, do things like sweep, change the output power and all these things. And it tells you all the information about how well it is powered, so that if you're running it from USB, make sure you have a good power supply coming in. And then they have a live measurement going on over here. So you consider that if you're using a synthesizer in the lab and you just want to get an LO out for your system, and this is just so much more convenient, so much more compact, you can stack them. So in terms of testing, system testing, and dropping it into something, I really like these. So we're eager to do it. I'm probably going to do a proper full review and analysis and teardown of this sometime in the future. But in the meanwhile, that's a pretty cool new product. So here we have a G-band measurement setup. Now, normally, a Y-factor measurement setup is going to assume a 50 ohm impedance into your device under test. It is well known that a tuner and an S-parameter calibrated setup is going to give you significantly better repeatability and precision of noise figure. But that's always a pretty difficult thing to do at higher frequencies, especially at G-band. So you need things like switches, noise sources, remote tests for S-parameter measurements, and of course tuners. So here on Focus Microwave, we have this G-band tuner in the front. You can see the G-band tuner directly connects to the probe, limiting any of that uncertainty, and then it is going to into a switch that allows you to switch between an S-parameter head. So here you can do your S-parameter calibration, part number one of doing the noise characterization, and then you have a noise source over here which then goes through the tuner, allowing you to completely extract all of the noise parameters. On the other side, there is a down converter. So depending on the head that you are connecting on the other side, you can have down conversions to different frequency bands. So in this one compact setup, the key is that because of the automated switches and everything completely being in place, you're not changing the setup at all between doing your noise figure measurements and noise parameter extraction, as well as the S-parameter calibration. It's done all in one step. So allowing you to do these, really, really broad noise figure characterizations. And if you have multiple bands in a row, then you can stitch them. And when you stitch them at the interfaces between, let's say, D-band and G-band, then you're going to get a really nice transition because you have the entire noise parameter. So these systems are becoming a little bit more common and nice and compact here from Focus. So here at Focus Microwave, we have the rapid load pull system. So these systems are quite complicated because you are exciting the input and the output of the DUT with your custom waveforms, in this case fully modulated, in order to emulate different points on the Smith chart. You're doing an active load pull system. So this is based on a PXI from Keysight, so you have a complete direct digital synthesis DAC generating the waveform you want. It can be any waveform. And that goes into their box, which does all the conditioning in order to apply the signal to the input and the output of the DUT. And that signal is coming back from that box going to direct digitizers. So basically, you're doing a complete analysis by exciting coherently the input and the output and synthesizing all these complex DC kind of modulations. Now, imagine how many other things you can do once you run these correlations. So for example, you can almost emulate the entire Smith chart, so you're covering the entire load pull system. You can do this at the fundamental and even at the second harmonic to get that little bit of a return that you want on that. Remember, this is running completely on a modulated signals. So to give you an example of what kind of data they generate, it's really quite impressive because there's a tremendous amount of computation that's happening here. So here's the Smith chart space, all the different individual points. You select all the individual points. You see the waveform exactly at every instance. You can go to the second harmonics and look at that. And then you can plot all these contours. And these contours will give you For example, an EVM contour across the load pool. So you see where you get the best EVM from this particular Wi-Fi amplifier. You'll see what happens to the ACPR. You can look at what happens to the input and output power. So it is a full characterization. Now, considering how much computation is happening, each of these points can take about maybe 8 or 9 seconds. But then once you've done this, I mean, just consider if you wanted to simulate this even, it would take days at a time. So this complete system, all automated in the background, can do all that for you. So we also want to make sure that we appreciate the challenge here from the probing point of view. Look at how large these 4-axis manipulars actually are. Normally in a sub-terahertz or a high-frequency measurement, you do want a really big plate here because you have converters, you want to bring everything as close as possible, you want to mount everything as close as possible. But this has a lot of mass, and now you need planarization between your probe and between the entire probe station. That's a big challenge. Now, MPI has a huge range of probe stations, and in this particular one, they have these dampeners that are sitting on the left and right side of the probe, and they're bearing the weight of these large manipulators. So as you lower and raise the probe, these all move together, maintaining that really good repeatable contact. I mean, making noise measurements at G-band is hard as it is, but having all this mass actually work at the precision of the probe tip is no easy task. But you definitely want these large plates to be able to handle these. It's an impressive setup. So here is a few of these focused microwave tuners here, covering D-band, G-band, and Y-band. And one of the cool things about these is that they do have the built-in couplers. So normally when you have these kind of tuners, you may have to add a coupler on top, but having them all integrated in one place with connections directly accessible, of course, it removes measurement uncertainty, allowing a much more compact measurement. So here at Siglent, I wanted to talk a little bit about their kind of portfolio of handheld devices, because they've been putting a lot of effort upgrading and providing new features in their portable devices. So they have these network analyzers, full 2-port capability with spectrum monitor. This is a 26.5 gigahertz 2-port version over here with reasonably good dynamic range for a handheld device like this. And then they have their new 7.5 gigahertz real-time spectrum analyzers that has a 1-port or a one-way S parameters. You can measure S11 and S21 in vector, but it does have 110 megahertz of real-time analysis with about 3.5 microsecond of 100% probability of intercept. So it's interesting that the network analyzer with spectrum functions and spectrum analyzer with network analyzer functions, that gives you kind of an opportunity to pick which feature you really want to focus on. Apparently, this is also going to eventually reach 26.5 gigahertz as well, but because it does have the real-time and that digitizer, it also does some streaming in chunks of memory, so you can also stream data out and do demodulation outside of the instrument. But they have clearly taken the core technology in their spectrum and network analyzer and miniaturized them to some extent and providing all these handheld devices, competing with some of the bigger players in this domain. And of course, we have the large SNA 6000 series. Now, I actually have this in the lab, and we're going to do a proper teardown and review of this. But here you can see it coupled with the switch matrix, expanding the capabilities beyond 4 ports and doing all these complicated measurements. Now, all the software features that I've shown you, for example, iMonitor, you can see here for TDR measurements and spectrum monitor and everything else is available on this VNA as well with much, much larger dynamic range and capability. So the teardown analysis of this should be very interesting. I think there are higher frequency versions of this at some point coming out as well, but 100 kilohertz low cutoff frequency is a very nice addition. It's not just 10 megahertz, as well as these expansions. Once you add this switch port to it, it's controlled by the system altogether, and it becomes abstracted away as a multi-port system. So we're very eager to take a look at this in more detail. So here at LeapWave, I want to show you an interesting new technology. So there is a fundamental problem with being able to generate really, really broadband signals or detect them in instrumentation in particular and other applications. So let's say you want to build a network analyzer that goes from DC to 500 gigahertz. You need to generate, transfer, transition that into whatever system you want to measure. So here, what they have developed is that currently they're using 2 DFB lasers, and they are shining them onto the same photodetector, or that mixes them together and generates a signal. That's a well-known topic and a well-known phenomenon. But then that signal coming in has a huge frequency range. So they have these unique transitions that they have created, allowing them to work at these ultra high range of frequencies. So they have 2 demos here at the same time. Here, there's 2 wavelengths going in, creating a broadband signal sweep going into a detector here that gives you kind of a power, because we can't measure up to 500 gigahertz that easily. And on this side, they have the Anritsu's nonlinear transmission line-based spectrum analyzers that goes up to 110 gigahertz and actually capturing the spectrum directly. So there's a lot of things that this can obviously be applied for, but instrumentation is immediately obvious because if you have a network analyzer, you want to be able to create that large frequency range. Now on the other side, when you have two lasers, you can do coherent detection at the same time. So if you have a photodetector on the other side and then you can do the mixing, well, now you have a coherent link, just like we do coherent communication. Now you have this huge frequency range you can detect and analyze, and that's pretty interesting. A few innovations on the signal generations and the innovations on the transition can enable these kind of systems. So here I have a very unusual flexible waveguide. Now traditionally flexible waveguides are of course useful when you want to connect things that have an unusual interface or things that are potentially moving or you're setting up. But this type of flexible waveguides typically have a lot of loss, and that loss obviously eats into the dynamic range of the measurement you're trying to do. And there's a certain rigidity and a certain lifetime that they may have. Now here we have a really interesting one. The inside of this, there's a dielectric waveguide. On that dielectric waveguide, the way the fields travel in a dielectric waveguide is they can actually extend beyond the boundary of the dielectric. So you have to have it float inside of the casing material you have, and that's why this structure is there. It's all custom made in order to do this. So as you twist it and rotate it around, it maintains that dielectric waveguide location inside of this entire cable. So something like this, I think 600 millimeters or so, between 3 to 4 dB of loss at D-band, 110 to 170, is really impressive, especially how flexible it is overall, with of course rigid waveguide connectors at the end. So this means you can now connect really unusual pieces together in an S-parameter setup, leave it, and then it will stay stable with really good loss, not eating into your dynamic range. Definitely one of the best performance flexible waveguides I have seen. So in the world of calibration, especially single sweep systems that go above 140 gigahertz, calibration is always going to be an issue. Now these single sweep systems are intended primarily for things like coherent optics, where you're trying to get above 200 gigabaud or so. So this is, from Spinner, is the only 0.8 millimeter traceable calibration kit that exists today. And in fact, this one does go all the way up to 167 gigahertz. So with this traceability, now you can calibrate your coaxial interface, which is needed for these broadband optical devices that people are making, and then cal all the way to 167 gigahertz, and then get a single sweep measurement with traceability in there. And they also have launch connectors like this that allows you to launch directly onto a PCB. Again, these coaxial connectors are critical for this next generation of optical devices. So having something like this, I mean, for new generation of this, it's just inevitable. Somebody has to be able to do this traceable cal so you can characterize these next generation optical components. So here at Eravant, there's always something new and some new modified to their existing lineup. This is a standalone 22 gigahertz synthesizer box, and with a nice display over here. The compactness of this allows you to combine it with some of their multipliers. So here they have an E-band. There's a 60 to 90 gigahertz multiplier. Very, very small form factor with the USB-C connections on the side that has all the calibration coefficients built in. So you can extract them and find out what exactly the output power is, a measurement plane. This one is also equipped with an isolator, attenuator, a transition, and a waveguide antenna over here, making a complete, super compact E-band signal generator, with reasonably good output power. On the other side now, they have also upgraded some of their detectors. So this particular one here now has a diplexer built in, so it can connect to things like Anritsu directly from there. And yeah, they're transmitting something across. So here we have the second generation of E-band remote heads from Eravant. So these guys actually extend the frequency range a little bit beyond the typical W-band frequency range, so from 67 to 116 gigahertz in the same WR10 waveguide interface. Now, Eravant makes their own devices. They essentially engineer this thing from end to end, allowing them to lower the cost quite a bit. So apparently these things, a pair of these is $30,000, which is a lot less than what's on the market. The output power about 7 dBm, compatible with a variety of waveguide, variety of coaxial interfaces for network analyzers. We have one of their kind of electromechanical style of attenuators where you can rotate things from the inside. You can actually see what's going on in here. So yeah, this low-cost version of these E-band with the extended frequency range definitely makes them a good competitive solution. So if you've been watching the channel, you definitely have seen the extensive review of the SM200C and SM435C. This is a 20 gigahertz real-time spectrum analyzer. And now they also have a 20 gigahertz vector signal generator that pairs with it really nicely with a 40 megahertz of arbitrary waveform bandwidth that you can apply anywhere on the band, with a free software that sits on top of it. You can generate all kind of different standards and modulations and everything. Now you can pair this guy with this guy and put your device on the test in the middle. You can do wireless, you can do whatever you want, and now you have a complete closed ecosystem covering the entire frequency range. Having the free software for all these different modulations is an enormous advantage in getting a quick system built and set up and easily tested. And you can, of course, close all this in the same software platform. And a closer look at this unit, you can see it also has a new body styling, the same secure USB-C connections and everything. And these guys are going to be available sometime in the fall into full production. And then, yeah, you should be able to order it directly from their website. So here we have the phase noise analyzer, and one of the advantages of having the multiple versions or multiple copies of these real-time analyzers is that the theory for phase noise analysis is cross-correlation. And because these are completely independent synthesizers and completely independent LO architectures, if you get your signal and fit it into this box that does the appropriate division between the two of them, and if you have a software running, you can do a cross-correlation phase noise measurement. And in fact, they can go down to almost minus 180 dBc of phase noise measurement through the correlation techniques over here. And one of the other things you can do is this itself is connected to the Spike software, so it has a control voltages, so you can do complete VCO characterization. That's a really critical aspect of it, because you cannot do cross-correlation phase noise unless you can lock a free-running VCO to do that measurement. And the nice thing about this is that once you're done with your phase noise, you'll just disassemble it and you get your spectrum analyzers back with all the capabilities, and you can switch back and forth between spectrum analysis and phase noise analysis directly here on the Spike software. This is a very different approach to doing phase noise, because you're not kind of holding up an instrument for a very dedicated measurement. You just mix and match as you need to. It's just the strength of the modularity of the system. So now, building on the same philosophy of portability that Signal Hound has, here we have a 40 megahertz to 40 gigahertz two-port network analyzer that is entirely powered from a single USB port. I don't think I've ever seen a system that can run from a single USB port and cover this kind of frequency range, 132 dB of dynamic range. It supports all the programming interfaces like Skippy. It supports all the mechanical calc. It's completely open for that. And it also has a variety of eCal modules, this one from Mari, that you can use to do this. Now, this kind of fits in the same philosophy that if you have some measurements you need to do around the lab, or if you need portability and you want to bring a network analyzer up to 40 gigahertz with you that doesn't need anything except for a USB port to work, well, this is definitely one of the options that I don't think I've ever seen anywhere else before. And this fits nicely into the ecosystem of everything else they're doing. If you look at the complete portfolio of Signal Hound now, they're beginning to capture more and more of the variety of measurements you want, but all of them built on these super portable, easy-to-use devices. So when it comes to load pool device characterization, you have focused microwave heads that allow you to adjust the load pool of a device. You can characterize the device and extract those models for validation. But then on the step afterwards, you can do this new thing that Dassault is doing, which is this RF pulse IV characterization. You basically apply an RF pulse that has the envelope characteristics of the signal you want the device to process under the load conditions you want it to process. And then at that point, you do your IV characteristics. So any unusual things that happen in the device due to trap effects will actually be captured because of that RF pulse now being applied. So you have a two-step measurement where you've done a complete load pool, you save that, then you do your RF pulse measurement, you combine that, and then from that you can do your validation, you can do your parameter extraction, but then you will see the exact dynamic behavior of a system. So something like this is really a combination of obviously the tuners and a whole bunch of software that goes in the back. Now you can take that software, even throw it into a neural network, and then extract some unusual characteristics or just model the whole thing in a neural network. Now you have the dynamic characteristic, and that neural network can predict what happens to your device in a much more complicated scenario. So a combination of tuners, the software, and the Dassault's applications running on top gives you this insight into the dynamic behavior of these devices. So here at VDI, we continue to see them push these kind of system measurements up to a higher and higher frequency. Here we're looking at a system between 330 and 500 gigahertz. This is a WR 2.2 system. Now what they want to do here is they want to show the capability of their remote heads combined with the Keysight instrumentation to actually characterize these devices at these crazy high frequencies with very, very high modulation bandwidths. Now this is using a technique that combines an arbitrary waveform generator from Keysight with a frequency stitching EVM assessment that PNAX can do. This itself is a completely different measurement system where you have to do basically stitching the frequency characteristics by using an S parameter measurement as a reference, and then from that you extract the EVM characteristics of that modulation. Now this is pretty useful because if you have a very, very high bandwidth, let's say you're doing an occupied bandwidth of 20, 30 gigahertz around this frequency, you don't want to have a digitizer. You can do this directly using the PNAX and the VDIS at the same time. Some of the numbers they hit is genuinely impressive. I mean, if you look at the EVM measurements, for example, on the 64 QAM modulation, we are sub 1% at carriers in the hundreds and hundreds of gigahertz, enabled by this entire ecosystem. Now you've seen, of course, me talk about a lot of these VDI modules in the past, all of them designed and made by themselves, and continue to push these higher frequencies. Another thing that is really important is that VDI works with big test and measurement companies like Keysight, enabling their softwares to be embedded directly in the measurement system, getting these extraordinary EVM measurements at the same time. And here's a closer look at the Keysight VSA doing this modulation analysis, and you can see that we're talking about 72 gigabit per second at a carrier in the between 330 and 500. And if you look at EVM as a function of symbol, I mean, it is pretty steady, showing a certain stability of the system. And here's the the main number, EVM 0.8%, which is really quite impressive. SNR 38 dB, very good. So here at VDI, I also want to show you something interesting, which is their latest ultra-high power TR headsets for S-parameter measurement. This particular one is WR8, 90 to 140 gigahertz. So traditionally, network analyzer heads have always been limited in output power, particularly at these frequencies, especially if you cross 100 gigahertz. And the problem with that is, well, if you don't have a lot of output power, you cannot, for example, compress amplifiers that you connect to DUT cannot be compressed so easily. Or if you have losses in your system, then you're eating into your dynamic range. It will become very difficult to measure. Now, VDI has been making high-power amplifiers for a very long time, and inside of this TR headset is an 8-way power combined indium phosphide HPT system that gives you a watt of output power between 90 and 140 gigahertz at the test port, which is a huge amount of power. In fact, this module you see here is something that's already inside, and this kind of amplifier has about 25, 26 dBm P1 dB and 30 dBm of PSAT, and they're just measuring it. And with the combination of PNAX, you can do P1 dB and PSAT of this device, easily compressing it with this kind of amplifier. You can imagine if you're doing things like load pool, or if you have amplifiers that need a lot of input power to compress them, how would you get that without having 30 dBm at the test port? Now on the other side, remember that if you're generating 30 dBm here, you have to be able to accept 30 dBm in the other side, because otherwise you won't be able to calibrate with a through. So there are mixers on the other side and couplers that are optimized for just the right amount of coupling to maintain the dynamic range you want on the receiver while being able to accept that 30 dBm incident power into the TR headset. I think this is the first time I've ever actually seen a 1 watt TR headset here, using completely end-to-end custom design indium phosphide devices to be able to do this. But these high-power kind of the TR headsets are going to be the de facto for both active measurement as well as passive measurements in these really high frequency ranges. So here at TransSiP, let me show you something interesting. So generally speaking, DC-DC converters obviously are going to have a huge amount of noise on them depending on the clock frequency running on the DC-DC converter. Even in spread spectrum situations where they try to eliminate some of these tones, you will still end up in a situation where you have a raised noise floor directly coming from your DC-DC converter. Now, whenever you want to feed a sensitive system with a dirty power like this, you are going to have some of these signals up-converted to your carrier. It's impossible to feed a very sensitive PLL or a sensitive synthesizer with a dirty clock and not see the effect of that. So the solution is what? The solution is obviously to filter your DC-DC converter in some way, and there's an actual example of where their product sits. So here we have the ADI's Gen 3 silent switcher. It's a pretty popular part, and then it's going to have some certain noise associated with it, even though this itself is a pretty good part. And then they have their product right over here. It sits directly in the path of the power supply. In fact, it can support up to 6 volts and 5 amps. It's a very, very small part. And from what they tell me, it's in a combination of some proprietary ceramic organic material, allowing you to completely filter everything from the power supply. Now, once you filter that, all you need to do is to drop this in front of your DC-DC converter, then connect that to whatever else, and yeah, you can see the harmonics in the signal are all cleaned up. Now, this is a very interesting process. I've actually never seen this type of material before, so I'm eager to learn more about it. But if they look at the size of this, I mean, this thing is tiny. And if supporting 5 amps, 6 volts directly in front of your DC-DC converter, seems like a no-brainer. So I'd definitely love to learn a little bit more about this, but keep an eye on this as one of the devices that have been released here at IMS. So here I am at Microsanj. Now, in the past, I have recorded videos about their thermal reflectivity systems. Now, what they're doing over the years is that they're looking at ways to leverage their thermal management and thermal measurement systems to extract some new ways of looking at circuit flaws and circuit performance. So consider, for example, a circuit like this, fully assembled, and there is a break or a disconnect somewhere in the system. Now, you can excite different traces on this and look at the thermal reaction of those traces. Now, if you have an open circuit, the dissipation of that thermal will be different on a circuit that's actually making connection. Now, remember, we're talking about minute differences in temperature. So the measurement system now has to be able to resolve extremely small changes in temperature. But if you can do this, now you have a completely unique way of measuring flaws and disconnections in your system. You're looking at a thermal signature of a physical problem by exciting the circuit and looking at what happens. There's a lot of really interesting things that Microsanj does by doing this kind of signal processing, and I'm eager to get my hands on one of their thermal reflectivity systems so we can cover both the science and what you can do with it in a real environment.
And there you have it. I hope you enjoyed this little snippet of the industry showcase. Next year, the conference will be held in Boston on the East Coast of the United States, and I hope to see you there.